Welcome to DAR Tutors. Today, we're beginning a new chapter on matrices. This topic is essential for your IB applications and interpretation higher-level exams and forms the basis of many real-world applications, from computer graphics to economics. In this video, you will learn to understand the structure of matrices, perform basic matrix operations like addition, subtraction, and scalar multiplication, and apply the rules of matrix algebra. Our main learning objectives are to define and identify matrices and their order, perform addition, subtraction, and scalar multiplication on matrices, and solve matrix equations. A matrix is simply a rectangular arrangement of numbers or elements in rows and columns. We can represent a matrix using square or round brackets. The horizontal lines of numbers are called rows, and the vertical lines are called columns. For example, consider Akriti's stationery shop, which sells 2 brands of pens, Pentex, and Rollerball in 3 colors. We can represent her sales data in a matrix. The table shows sales for blue, black, and red pens for each brand. We can convert this directly into a matrix Q. Here, the rows represent the colors and the columns represent the brands. Notice how the structure of the data is preserved within the matrix. Now, let's talk about a matrix order. The order of a matrix is defined by the number of its rows and its columns. We write the order as m by n, where m is the number of rows and n is the number of columns. This is often abbreviated as mxn. So, a matrix with m rows and n columns has an order of mxn. Remember, it's always rows first, then columns. For our pen sales matrix Q, we can see it has 3 rows and 2 columns. Therefore, its order is 3 by 2. We can refer to a specific element within a matrix using its position. We use the notation A sub ij, where I is the row number and j is the column number. For instance, A sub 1, 2 refers to the element in the first row and the second column. In our sales matrix Q, Q sub 1, 2 is 24, as it's the number at the intersection of the first row, blue pens, and second column, rollerball. Similarly, Q sub 2, 1 is 25. Matrices can also be vectors. A column matrix or column vector has only one column, like a 4 by 1 matrix. A row matrix or row vector has only one row. A special case is the square matrix, which has an equal number of rows and columns. A 3 by 3 matrix, for example, is a square matrix. In this scene, we've defined a matrix order and how to refer to its elements, meeting our first learning objective. This understanding of structure is critical for all further operations. Now let's move on to comparing matrices. 2 matrices can only be equal under strict conditions. The rule for matrix equality is straightforward. For 2 matrices, A and B, to be equal, they must satisfy 2 requirements. First, they must have the exact same order. Second, every single element in the corresponding positions must be identical. A equals B if and only if a sub ij equals b sub ij for all I, j. This means you cannot have a 2 by 2 matrix equal to a 3 by 3 matrix, and you cannot have a 2 by 2 matrix equal to another 2 by 2 matrix if even one element is different. For example, if we have these 2 by 2 matrices, for them to be equal, the element A must be equal to W, B to X, C to Y, and D to Z. Every pair of elements in the same position must match. Let's apply this concept to find unknown values within matrices. Here is an IB-style problem. Suppose we have this matrix equation. Our goal is to find the values of x and y. Since these 2 matrices are stated to be equal, we can use the definition of equality. This gives us a system of equations by comparing corresponding elements. From the first element in each matrix, we get the equation x equals y. From the 4th element, we get a second equation. -1 equals y plus 1. Now we can solve this system. Solving the second equation gives us y equals -2. Substituting this back into the first equation, we find that x also equals -2. The solution is x equals -2, y equals -2. We've now seen how the strict conditions for matrix equality allow us to solve for unknowns by setting up a system of equations. This is a fundamental skill for matrix algebra. Next, let's explore matrix addition and subtraction. These operations are essential for combining or comparing data stored in matrices. The first and most critical rule is that you can only add or subtract matrices if they have the exact same order. If they don't, the operation is undefined. Provided the matrices are the same size, the process is very simple. You just add or subtract the elements that are in the corresponding positions. This means you combine A sub ij with B sub ij. Let's use an example from a clothing store. Thao has 3 stores, A, B, C, and we have a matrix showing her current stock levels for dresses, skirts, and blouses. This is her current stock matrix. Notice its order is 3 by 3. Now Thao gets a new delivery. 20 dresses, 30 skirts, and 50 blouses for each of her 3 stores. We can represent this new delivery with another 3 by 3 matrix. Its order is the same as the stock matrix, so we can add them to find the new stock levels. To add them, we combine corresponding elements. The element in the first row, first column of the new stock matrix will be 23 plus 20, which is 43. We do this for all 9 elements. This results in a new matrix of the same 3 by 3 order, showing Thao's updated stock. Matrix subtraction works the same way. We subtract the corresponding elements. If Thao started with a different stock matrix and then had these sales, the remaining stock would be found by subtraction. Again, the result is a matrix of the same order. We've now mastered matrix addition and subtraction, fulfilling another part of our second objective. Remember the golden rule. Same order, then combine corresponding elements. Our next operation is scalar multiplication. A scalar is simply a regular number, or a constant. When we perform scalar multiplication, we are multiplying a matrix by a scalar. The process is incredibly straightforward. To multiply a matrix A by a scalar k, you multiply every single element within the matrix by that scalar. The order of the matrix does not change. Let's use a pantry example to illustrate. Suppose we represent the contents of a pantry with this column vector. This vector C shows 6 cans of tomatoes, 4 cans of beans, and 8 cans of fish. Now, what if we needed to triple the contents of the pantry? Tripling the contents means we want to calculate 3 times the matrix C. We do this by multiplying each element inside the matrix by 3. The resulting matrix, 18, 12, 24, represents the trebled contents. 18 cans of tomatoes, 12 cans of beans, and 24 cans of fish. The new matrix has the exact same order as the original. We can also multiply by fractions or negative numbers. For instance, to find half the contents, we multiply by the scalar 1/2. Multiplying each element by 1/2 gives us a matrix representing half the original amount. This operation is incredibly versatile. It allows us to scale data up or down, or even reverse its sign. We have now covered scalar multiplication, completing our second objective of performing matrix operations. Now that we know how to add, subtract, and scalar multiply matrices, let's explore some fundamental rules of matrix algebra. These rules will feel very familiar to anyone who has done ordinary algebra. Just like with real numbers, matrix addition has some important properties. First, it's commutative. This means that if you have 2 matrices, A and B, of the same order, A plus B will give the same result as B plus A. The order of addition doesn't matter. Second, it's associative. This means that when you add 3 or more matrices, the way you group them doesn't affect the final sum. You can add A and B first, then C, or add B and C first, then A. For example, if we have these 2 2x2 matrices, A and B, adding A plus B gives us one result, and adding B plus A gives us the exact same result. This visually confirms the commutative property. Let's also introduce 2 special types of matrices that behave just like the numbers 0 and 1 in ordinary arithmetic. First, the 0 matrix, denoted by a bold O, is a matrix where every element is 0. When you add a 0 matrix of the correct order to any matrix A, the matrix A remains unchanged. This is similar to how adding 0 to a number doesn't change it. Second is the negative matrix, denoted by negative A. This is the matrix you get by multiplying A by the scalar 1, which means you change the sign of every element. When you add a matrix to its negative, the result is always a 0 matrix of the corresponding order. For example, if A is this matrix, then its negative, A, is found by changing all the signs. And when we add A and A, we get a 2 by 2 0 matrix. These properties, Commutative, associative, and the existence of zero and negative matrices are the building blocks of matrix algebra. We've now established these fundamental rules. We can use the properties we just learned to solve for an unknown matrix in an equation. This process is very similar to solving a linear equation in ordinary algebra using inverse operations. Let's work through an example. Suppose we have the equation x plus a equals b, where a, b, and x are all matrices of the same order, and x is the matrix we want to find. We want to isolate x on one side. In ordinary algebra, to get rid of a plus a, you would subtract a. Here, the inverse operation is adding the negative matrix, a. We add negative a to both sides of the equation to maintain balance. On the left side, a plus negative a simplifies to the zero matrix O. On the right side, we get b minus a. Finally, adding the zero matrix to x leaves us with just x, so we found that x is equal to b minus a. The method mirrors that of real numbers. Let's do a concrete example. We need to find a matrix x such that a minus 2x equals 3b. We have three 2 by 2 matrices and an equation. Let's solve for x step by step, just as we would in ordinary algebra. First, we rearrange the equation. We add 2x to both sides and subtract 3b from both sides. This gives us a minus 3b equals 2x. Dividing both sides by 2 is the same as multiplying by the scalar 1/2, so x equals 1/2 times the quantity a minus 3b. Now we calculate the matrix expression. First, we find 3 times b by scalar multiplying every element of b by 3. This gives us the matrix 3, 12, negative 3, 3. Next, we find a minus 3b by subtracting corresponding elements. 1 minus 3 is negative 2, 0 minus 12 is negative 12, and so on. The result is this 2 by 2 matrix. Finally, we find x by scalar multiplying this result by 1/2, giving our final answer for matrix x. This example shows that matrix algebra can be used to solve equations in a logical step-by-step manner. We have now covered the fundamentals of matrices. Before we move on to practice problems, here is an important message. If you found this video helpful and are looking for expert personalized support for your IB, A-Level, or IGCSE studies, I encourage you to contact DAR Tutors. Our team of experienced tutors provides high-quality online and in-home tuition tailored to your specific needs. Let us help you achieve your academic goals. You can find our contact information at the end of this video. To recap, we've learned how to define and structure matrices, including understanding their order and element notation. We've mastered the operations of addition, subtraction, and scalar multiplication, and we've applied the laws of matrix algebra to solve equations. These are the foundational concepts you need to build upon for the rest of this unit. Now, let's put your knowledge to the test. We will go through 5 IB-style practice questions with fully worked solutions. Pause the video, try them yourself, and then review my solutions. Here is your first practice question. Pause the video here and attempt the problem. Welcome back. Let's start with part A. The operation is A plus B. First, we determine the order of each matrix. Matrix A has 2 rows and 3 columns, so its order is 2 by 3. Matrix B has 3 rows and 2 columns, so its order is 3 by 2. What is the rule for matrix addition? That's right, the matrices must have the same order. Since 2 by 3 is not the same as 3 by 2, the operation A plus B is undefined. We cannot add them. Now for part B, A minus B. Since the rule for subtraction is identical to addition, they must have the same order, and we've already established their orders are different. A minus B is also undefined. Finally, part C2A plus B. Here we have a scalar multiplication and an addition. First, let's consider 2A. Scalar multiplication does not change the order of a matrix. Since A is 2 by 3, the resulting matrix 2A will also be 2 by 3. Now we are asked to add this new matrix 2A to matrix B. The order of 2A is 2 by 3, and the order of B is 3 by 2. Just as in parts A and B, these orders are not the same. Therefore, the addition 2A plus B is undefined. Here's your second practice question. It combines scalar multiplication and subtraction. Take a moment to solve this one. Let's work through the solution. The problem asks us to find the matrix X by calculating 3 times A, then subtracting 2 times B. This involves 2 scalar multiplications and 1 matrix subtraction. Step 1 is to find the matrix 3A. We substitute the values for A and multiply every element by 3. This gives us the matrix 3, 9, 6, 0. Step 2 is to find the matrix 2B. Similarly, we substitute the values for B and multiply every element by 2. This results in the matrix -4, 2, 8, 10. Step 3 is to perform the subtraction. Now we substitute our results back into the equation x equals 3a minus 2b. Both matrices have the same order 2 by 2, so the subtraction is defined. We subtract the corresponding elements. 3 minus -4 is 7. 9 minus 2 is 7. 6 minus 8 is -2. And 0 minus 10 is -10. Our final answer for matrix X is 7, 7, -2, -10. Question 3 is another problem where you solve for an unknown matrix X. Pause the video and try to solve for X. Okay, let's solve this equation for X. We need to isolate X. The first step is to rearrange the equation to get 2x by itself. To do that, we subtract the matrix B from both sides of the equation. This gives us 2x equals A minus B. Now, to solve for x, we multiply both sides by the scalar 1/2. So x is equal to 1/2 times the difference between a and b. Now that we have an expression for x, we can calculate it in 2 steps. Step 1 is to find the matrix difference A minus B. Both matrices are 2 by 2, so this is possible. Subtracting corresponding elements, we get 3 minus 1 is 2. -1 minus 4 is -5, and so on. The result is the matrix 2, -5, -2, -3. Step 2 is to find 1/2 of the result from step 1. We multiply every element by 1/2, so 1/2 times 2 is 1, 1/2 times -5 is -2.5, and so on. Our final answer for x is the matrix 1, -2.5, -1, -1.5. This problem reinforces the process of isolating an unknown matrix using our rules for addition and scalar multiplication. Question 4 is a word problem that asks us to represent data in matrices and perform an operation. This is a common IB-style application. Pause the video and try this problem. For part A, we need to create 2 column matrices. A column matrix has 1 column and multiple rows. For December's sales, we'll put the numbers for hatchbacks, sedans, and SUVs into a 3x1 matrix D. For January's sales, we'll do the same to create matrix J. These 2 column matrices now concisely represent the data. For part B, we need to find the total sales using matrix addition. This means calculating D plus J. We check the order. Both are 3x1, so the addition is defined. We add the corresponding elements. 15 plus 10 is 25, 22 plus 18 is 40, and 8 plus 12 is 20. Now we must explain what the resulting matrix represents. This new 3x1 matrix represents the total number of each type of car sold over both December and January. The first element, 25, is the total hatchbacks. The second, 40, is the total sedans. And the third, 20, is the total SUVs. Matrix addition in this context allows for a clear and organized summary of combined data. Our final practice question is another application problem that combines scalar multiplication and subtraction. This is a great test of everything we've learned today. Pause and try this multi-part problem. Let's begin with part A. The store plans to increase its stock by 20%. An increase of 20% means the new stock will be 120% of the original stock. We can represent 120% as the decimal 0.2. So we need to calculate 1.2 times S. We multiply every element in matrix S by 1.2. For example, 1.2 times 120 is 144, and so on. The result is our new stock matrix, N. For part B, sales were 10% of the original stock. This will be our sales matrix, Q. Similar to before, we convert 10% to the decimal 0.1. So the sales matrix Q is found by multiplying the original stock matrix S by the scalar 0.1. Multiplying each element of S by 0.1 gives us our sales matrix Q. Finally, for part C, we need to find the closing stock matrix, C. This is found by taking the new stock matrix, N, and subtracting the sales matrix, Q. We substitute our matrices n and q, and then subtract the corresponding elements. For example, 144 minus 12 is 132. Performing this for all elements gives our final closing stock matrix. This question demonstrates how matrices are used to model changes in inventory over time. We've now reached the end of our introduction to matrices. You've seen the fundamental concepts and how they are applied in IB-style problems. A strong grasp of these basics, structure, order, equality, addition, subtraction, and scalar multiplication, is crucial as you advance to more complex topics like matrix multiplication and inverse matrices. Thank you for watching. Remember, if you're seeking additional support or personalized tuition, DAR Tutors is here to help you succeed. Visit our website or contact us to learn more about our programs for IB, A-Level, and IGCSE students. See you next time. Need expert tuition for your IB, A-Level, or IGCSE studies? Contact DAR Tutors for personalized, high-quality tuition.